Okay, thank you everybody. Last but not least, it's a real pleasure to be here, and I'm a horticultural data scientist at Plant and Food, working at the Quantitative breeding program, doing increasingly complex quantitative genetic workflows. So it's sort of really hard to be the last speaker in a meeting like this, but it's sort of quite nice to be bookended with Chris. I think her presentation about the challenges in technology for putting together complex tools to do scalable work is a really big issue for us. I'm sort of picking up another aspect of that. So yeah, my co-author Roy Story helped with a lot of the config, but so overall just talking about the general challenges we face that Chris outlined very well as well, talking specifically about task graphs. I'm focusing on the R targets package because we're predominantly R focused people here, but there are a number of other task graph solutions. And I'm once again you're talking GWAS Poly, so this is not talk is not about GWAS Poly, but it's using Jeff's excellent vignette as an illustration of how to use targets and achieve some of the orchestration and parallelization with whatever hardware we've got. I've put this into a GitHub gist, which you can find from this bit.ly link, GWAS Poly target slurm. We might put it somewhere else if we can work out where. You can go to this gist and clone it like any GitHub repository and play with this. So what are we trying to do? Well, we've heard a lot about all these fantastic tools. We're trying to compose together really quite complex data, get it into a fit state, use one tool and then another tool. It's complicated, and then we inevitably things happen. We get more and more data. We want to execute it in finite time, respond to input from colleagues, questions, and we go back and have to change things. And we love working with things like R Markdown with notebooks. They don't really scale. So the alternative approach to the kind of linear notebook or script approach is to use directed acyclic graph representation. So the make function, classic Unix build function, is the classic example of this. But in a DAG, every node is an object. In our world, it's a data structure of some sort, and the edges are functions that we apply. So we want to basically run a function, a make function that'll only execute the nodes, the functions. To update nodes that need to be done. And we've got some kind of caching to preserve state. And this is a really important thing. So rather than just having some dynamic notebook and having to rebuild everything every time, you've got some caching on disk. So why the targets package? Well, the targets package was designed for people like us, people who want to do complex data engineering. This is what we're doing increasingly. And we want to do a lot of bigger and many models. So the developer, Will Landau, based at Eli Lilly, he really wants to just fit lots of Bayesian models. It's really great for us. It's make-like, it's R-orientated. There's some very good Python workflow packages as well that are available. Some of you may have come across Drake, but they made a lot of enhancements to targets. And the caching is really nice. It's really tidy, and you can cache all sorts of objects, including object storage on S3, for instance, high performance tabular formats, and so on. There's a lot, importantly for us, there's a lot of really nice integration via two packages: the future package, which I'll talk about, and the ClusterMQ, which is very nice. But I won't talk about. The documentation is great, and it's all on our OpenSci. So there are two components. There's targets, which is the core, and then target types, which is using a lot of R metadata programming to allow you sort of creation of custom objects, custom storage. So here's a graph representation of Jeff's vignette. So a number of steps. These are defined as objects in there. Starts off building a GWAS Poly object, and then he goes down two paths, basically that are differ by the nature of how the random polygenic effect is calculated, with or without leaving out one chromosome, putting that data together, and then generating an R Markdown report. So really the first, so what we do in targets is decompose this into a set of nodes, a set of objects. And this is written into the core of a targets workflow is an underscore targets.r file. And it heads off with sort of loading up whatever objects or packages that we want to sort of create the initial state, and then defining a series of objects with the syntax shown here. And in this case, we're starting off by tracking a couple of files, which are the inbuilt file, data files in the package. In a real life situation, this could be a file on disk. If it changes, it triggers the pipeline. And then in the second, the third object here, we're defining the read GWAS poly state. We've defined a dependency on these two previous objects, and we read this to create the data, the GWAS poly data file. So if we look at this we're looking at this more from the console. One thing that really goes without saying, environment management in this kind of for this kind of work becomes really important. If you don't use REN, you should learn about it. But we can execute this pipeline by going tar make, and we get some messages, so telling us it's starting to build these targets, telling us what it's doing. There's a bit of standard output here. So an important point about this is running in a separate R process. And this is really convenient for a lot of incremental development, because you're not sort of, you don't suffer the risks of having stray objects in your environment, not knowing what the state of it is. And we get a message at the end. So we've just asked to specifically build this data, which involved building these previous steps. So if we look at these, the state of this directory on disk, this is a very simple, flat data structure, because GitHub just don't support any subdirectories. But we can see we've got this underscore targets directory, and this contains the cached objects. Now these have the same name, the file names, as our objects in the workflow. And these default to RDS are objects, but there can be custom formats. There's a whole lot of different things you could do here. So you could just open those up any way you want. They're not obfuscated in any way, as many workflow managers would do. So the reason I first made this sort of targets vignette, because I was quite interested in working out how to run targets pipelines like this, but with orchestration on workflow manager. In the case I'm going to be talking about is a Slurm workflow manager, but we've got a nice opportunity here to parallelize, because we've got these two different ways of calculating the polygenic effect. So how we can abstract away all of this orchestration is using the future package. If you're not familiar with this, I'd direct you to looking at the Futureverse website. It's very nice. But we've got, Jeff's allowed us to use multiple cores to parallel computing. So what we're aiming to do here is to run these two branches of the workflow in parallel, and then use all the cores that we can reasonably apply to each of those. So the key to this is just sort of changing the header of our targets file by adding a plan. So the beauty of the plan is this will depend on what your computing environment is. And so in this case, we have to apply, we have a template file, which just is basically a bit of code to help translate into specific, in this case, SBatch with the Slurm job scheduler. It says B sub there. Interestingly, we changed from the LSF job scheduler to Slurm, and it was really easy, just change the plan to run exactly the same kind of workflow with a completely different scheduler. And we can set some defaults here for, in this case, setting the job schedule, required job scheduler settings like job timeout and number of cores and so forth. But this is a really important idea that for different situations, we have different plans, and this depends on our particular institution, our particular computer. So, and then we can go, say we want to customize the resources for particular steps, say a particularly expensive computation, a really big matrix calculation, or something that really goes a long time, we can customize this. So in this case, we give an extra tar resources invocation here to say, well, we want more cores in this case. So in the first case, we were just executing the pipeline in sequential mode, just sort of running on the actual head node in this case. But if we execute by going tar make future, and as shown on the top line here, this is saying run it with the maximum of 2 workers. And then we see a series of messages here, and you can see that both of these 2 branches are started in parallel. If you check, as shown out on the right here in the on the Unix console, you can see these jobs running independently in what they're on. So, and we get the output from the standard output from both of those model fittings. And at the end here, we've got a step where we're rendering our R Markdown report. Now, this is sort of quite one of the very nice features of for organizing complex workflows like this, is really separating out the processing from the analytics and the documentation, if you like. So at the end of our _targets workflow, we invoke this tar render function, which renders our R Markdown. And inside the R Markdown file, we have to load up these objects from the cache, but then these references are tracked in the R Markdown. So if these change, our R Markdown will get invalidated and rerun next time. So this is really nice. You've got a clean separation, so your R Markdown is not full of all your data manipulation. It's about the QC, the inspection, the analysis, the documentation. So in summary, I think one of the best things that in my experience about targets is it really encourages good practice. So writing functions, writing tested functions, putting helper functions into R packages, consistent project structure, and really a functional approach. R is a functional language after all. A really important one is easing the cognitive burden. I think the sort of complexity of the type of work we do can really blow out. One of the really key things as well is it's really encouraged us to look at environment management. It's a lot more fiddly in R on HPC than it is for Python and other languages. I think one of the real advantages, though, is this ability to sort of allow you to focus more on writing the R code and not worrying so much about orchestration and parallelization and all the sort of background stuff. The caching is really valuable, especially when things fail, fall over, or they're just really expensive. You want to rerun your Markdown. You don't want to wait for things to compute for several days. There are other ways of doing this, like Xfun Cache RDS works really nicely. I think one of the really interesting things, the next step for us is really looking at other supportability, like using object storage on S3. There are other high performance table formats as well that I think would be really good for a lot of our statistical genetics. So there are a lot of ways of using this kind of tooling for our work. And sort of this is sort of, I guess, the more general, a common thing that we're doing on the right. Here's a series of expensive univariate BLUP calculations being run in parallel on the cluster. That's a sort of standard practice now. So it just allows us to do more models and bigger data without so many overheads. So thank you very much.